Guys, in this video, we're going to talk about how to calculate the binding energy of an element. Let's look at this iron 56, because in this binding energy per nucleon curve, we know that iron is here. It is like the most stable element. Okay, now let's calculate the binding energy. Remember, binding energy in definition is the delta E here. Delta E is E binding. It is E binding. It is going to be equal to mass deficit times the C squared. Yes? Okay, so now we are given the real mass of all the nucleus here and the protons here. And let's try to calculate this binding energy. Now this binding energy is going to be the total binding energy. It means I need this kind of amount of energy to split up the iron nucleus. Say what I'm doing is that I'm doing something like this. Now this is like the let's say that this is a proton and this is a neutron. And proton we use the red ball, and for neutrons we use the white balls here. Okay. So let's say that this is a iron nucleus. Um, Now we just ignore the electrons. Okay. Yeah. We look at the nucleons. Now, one neutron is called a nucleon. Remember that? Nucleon. And one proton is also called a nucleon. Okay? And this whole thing is called a nucleus. All right. So we are given the number here, the real mass of iron. And what we can do is that we can calculate the mass deficit. How do we calculate the mass deficit? Say that we have this kind of reaction. Our reaction now is that we want to split this iron nucleus into its components, protons and nucleons. What I want to do is I want to do something like this. I want to split them up. This is my final effect of this reaction. So on my left hand side is going to be the whole nucleus of iron, which has this mass. So my reactants is going to be the iron nucleus, which has the mass number here, 9.27 times 10 to the power of negative 26. Now my products in this reaction, my products is going to be the iron nucleons, something like this. We want to split the whole thing into its components. Okay, so now let's move on. We are given the proton mass and the neutron mass, and for iron 26 we know that it has 26 protons and 30 neutrons, and this is iron 56. Okay, so what we do is that we can calculate it. We can, let's see, we can do is we are showing the mass of the reactant side is here. The mass of the products is going to be a little complicated because we want to do something like this. The M products is going to be like 26 protons times 1 proton mass times 10 to the power of 27 kg plus 30 times 1.6749 times. So this is going to be the mass of all the protons, and this is going to be the mass of all the neutrons. And then we want to use our calculator to calculate it. Just give me a second. We have to use a calculator to calculate it. So one thing we have to know that to split this iron nucleus into its components, nucleons, like the separate ions, protons, and the neutrons, you have to get some energy, right? You have to gain energy to make this happen, because the iron 56 is a nucleus. It's a whole thing. You can consider it as the sleeping state of you. So you have to use the alarm to wake you up, right? Yeah, the alarm can consider it as the energy gained here. So let's see, 1.6726 is going to be, this part is going to be, this part is going to be something like this. And this part is going to be 30 times 1.6749. It's going to be 50.247. And we want to add them up together. Now remember, these two are paired with 10 to the power of negative 7 times 10 to the power of negative 27. But our iron nucleus has this 10 to the power of negative 26, not 27. So we want to convert it into the same kind of thing. So it is going to be, let's see, this is going to be plus 76. This is going to be 93 point something like this, right? Times 10 to the power of 27. And your iron is going to be 92.7 times 10 to the power of negative 27. So we want to do this, subtraction. So in the end, we have 1.0346 times 10 to the power of negative 27. Now this difference is going to be the mass deficit, MD, okay, MD. And then the energy that pairs with it is going to be E binding. E binding is going to be mass deficit C squared. It is going to be 10346 times 10 to the power of negative 27 times 3 times 10 to the power of 8 to the power of 2. It is going to be, let's see, 1.0346 times 9 times, it's going to be 9.3 times 10 to the power of negative 11 joules. So this is a total binding energy. This energy is the energy required to split this iron 56 nucleus into its nucleons. Remember, we're doing something like this. We're doing something like this here. So we need to gain energy to make this happen. Don't forget that. I really love my analogy here. It's like before, for the nucleus state, it's going to be you sleeping there, sleeping you. You're sleeping here, sleeping. So you are more stable. Okay, you're more stable. And then the alarm goes. The alarm goes. Think of the alarm as the energy gained to make you excited. So you wake up. Okay, you wake up. This is this reaction. Okay. So sleeping you plus the alarm to get a waking up you. Does that, when you are awakened, you have more energy than when you are sleeping. Makes sense, right? And this binding energy of the iron 56 is kind of a fixed value for it. It is like the property of this nucleus, right? And then we want to know the binding energy, E binding per nucleon, per nucleon, nucleon. What do we have here? Binding energy. We just calculated 9.3, right? 9.3 times 10 to the power of negative 11 per nucleon. How many nucleons does this like iron 56 have? It's got 56 nucleons, right? We can tell it from its mass number. The mass number of it is 56. So we can calculate the binding energy per nucleon of iron 56. So as you can see here, it is also a fixed value for this kind of nucleus. And then for uranium 235, uranium, it also has this kind of property. And then we calculated, we find out that this EB, the energy, binding energy per nucleon, binding energy per nucleon. Maybe we use binding energy per nucleon here. Maybe we use BE here. Is going to be lower than this one. Binding energy of uranium is going to be less than the 56 iron. Fe, okay? Binding energy per nucleon. So that we have something like this. So in that curve, yeah, let's use another to draw the curve. So for this curve, it's going to be something like this. This is going to be your Fe, and this is going to be your uranium. Let's make it like iron, maybe. Iron. And this is uranium. Does it make sense? Because we can calculate, iron has a higher binding energy per nucleon. And uranium has lower binding energy nucleon than that of iron. Make sense? And what does it tell you? It tells you that if kind of a nucleus has higher binding energy, like iron, higher binding energy per nucleon means that it is more difficult to split this nucleus. It means that it is more stable. It means that you are in this deeper state of sleep. You are going to need a louder alarm to wake you up. Does it make sense? So it has something to do with, fission and fusion has something to do with this. But in this video, I just want to explain clearly what binding energy is, like total binding energy is, and how to calculate the binding energy per nucleon, and how both of them are like the, the properties of a nucleus. So it is like, it has a fixed value and we can calculate it. And after we calculate it, we can draw this graph. Does it make sense?